All right, so a little low on attendance on Friday Fun Day. Many people are baseballing, right? Soccering. I'm not sure what Riley is doing. Normally he's with you. You left him. So anyway, this is being recorded. So as always, keep it clean there, Jacob. All right, so today we're going to do section 7.2 and 7.3. If you look in the book, which I'm sure all of you did before class, and look at those sections, your reaction should be, wow, that's a lot of material. How are we going to do that in one day? And the answer is we're not doing all of it. Your book, it covers a lot of its bases, mainly because like some of the stuff in these sections you could use in say chapter 10 or something. But what we need, which we'll need later in chapter 7 and then chapter 9, we don't need nearly as much as in the book. So this here, what we're going to do today is the bare minimum of linear algebra we need for our purposes in this course. So anyway, the book as a reference for these two sections is probably not great just because there's so much material there. Like 80% of it we don't need. Anyway, so the point of today is to just establish the basic notation and definitions of matrices that we'll need when we go back to calculus on Monday. So there's not going to be hardly any calculus today. No differential equations today, really. Okay, so linear algebra is a gigantic field of math which studies matrices. And matrices is a fancy, or a matrix is a fancy math way of saying a table of numbers or a table of functions. So this is a table of numbers right here. On here, right? It's a 3x2 table. That's all a matrix is. So when you hear matrix, just think table. You can think array if you like to think computer science wise. But linear algebra, you can study matrices a lot, it turns out. Linear algebra is a study of those things in their algebra, as you might expect, right? Okay, so anyway, the table has m rows and n columns. So m by n matrix, it comes with dimensions associated with it. M rows and n columns. You use capital letters to denote a matrix, and a given element is identified by its location in the table like that. So row I, column J, A sub ij is the entry at that spot. So in this matrix here, what is little a 1, 1? So like this, what if I put in a 1 for I and a 1 for J in this table here? What entry am I talking about? Yeah, right there, right? Row 1, column 1. So you can say A11 equals 1. Maybe I should do some of this over on the board. So I have to record this. So I'm always a little nervous about moving around. Let's see. Okay, so for that same matrix, what is like, I don't know, A2, 1. Row and column. Yeah. So what is it, sorry? 2, yeah. Row 2, column 1. Okay. So anyway, that's just a little shorthand for talking about entries of a matrix. Okay, a vector, as I'm sure many of you know from physics or whatever, a vector can be thought of as a matrix. It's simply an n by 1 matrix, which means there's only one column. So a matrix doesn't have to have more than one column. Like this one down here happens to do that. But if you have just one column, it's called a vector. Vectors have different notations associated with them, either bold or with an arrow over it. So of course, at the whiteboard, I can't do bold, right? That's really hard to do. You can't like write harder with a marker on a piece of paper or something. So normally I stick with this arrow over it. And the entries of E are denoted like this, V1, V2, and so on. You don't need 2 subscripts because it's not a 2-dimensional thing, it's just a single column. You can add matrices if you want to. So you just add them sort of component-wise. So just for example, and make sure this is. So somebody says, hey, add this. Here's a matrix. Here's another matrix. The definition says just add things component-wise. So the 2 matrices you're adding have to have the same dimensions. These are both 2 by 2, so that's all right. So the result is 2 by 2. What's the top left entry? Yeah, you just are like, oh, top left plus top left is new top left. That's all you do. And so on, right? 10, 2, and 5, like that. So adding matrices is not so bad. You just find the two corresponding entries, add them up. That's the new corresponding entry in the new matrix you just built. Matrix multiplication is not nearly as simple. It's much more complicated. So in general, you can multiply a big matrix by a big matrix, but for our purposes, all we care about is what if you have a general matrix and you multiply it by a vector? So like here's a general matrix multiplied by a vector. How do you do that? Okay, so if A is m by n and the vector is n by 1, and this is not a coincidence here, these two numbers do have to line up. If they don't line up, you can't do the multiplication. Multiplication is undefined. So this here, this is what? 3 by 2, right? And this is 2 by 1. Those twos have to match. If you add a 3 by 2 and then a 3 by 1 here, you can't do it. Like if you ask Wolfram to do it, it shrugs at you, says, I don't know what you want me to do. So anyway, as long as the number of columns here matches the number of rows here, you can multiply a matrix times a vector, and it's kind of hard to explain how to do it in text. Why I come in the handout and say, let's just do it on the board. So let's do this example here, this example 1. Have you guys multiplied matrices before? Okay, been a while or never, that's fine. Okay, so you write it like this. My compiler likes to do curly parentheses for a matrix. I like to do square when I write. It's just a stylistic choice. It makes no difference. You can write them either way. Okay, so this is A times B. You're okay with that? Okay, when you multiply like this, when you do m by n times n by 1, the result is something m by 1. So to multiply a matrix by a vector, again, you need a match here. And then what's going to pop out is going to be another vector. So the one right here, right, comes from this one. But the new vector may or may not have the same number of rows as the old vector. And in this case, it won't. So the m right here matches like that. So an m by n matrix times an n by 1 vector gives you an m by 1 vector. So here, I'm going to have 3 rows from these 3 rows. Are you okay with that? Okay, so the question is, well, what goes in these 3 entries, right? There's these gaps right here, you got to fill those in. Those are meant to be gaps, not buttons or not zeros. As I look at it, it's confusing me. You got it. Okay, so to fill in the top entry here, what you do is you put 1 finger here and 1 finger here. You multiply those 2 numbers. I'm going to do that. So 1 times negative 1. So finger here, finger multiply. Then you click this finger to the right and this finger down 1. So you're going to do this with your hands. This finger moves left to right. This finger moves down. And you multiply each spot your fingers are, you multiply the 2 entries. So multiply here. Then when you click your fingers, you add. So then you'll add 0 times 3. So the top entry of that row is the first row times this column, where by times I mean you're multiplying entry by entry and then adding as you go. It's actually a dot product, if you like that language. You're doing the dot product of this row with that column. You physicists like dot products, right? So matrix multiplication is just a bunch of dot products filling in the new matrix you're building. Anyway, so there's the top entry. Now for this middle entry here, what you do is, we were doing top row times this column. Now you just do middle row times this column. So your fingers are here. 2 times negative 1 plus 5 times 3. So you do the same operation, you just moved your left-hand finger down 1. So 2 times negative 1 plus now 5 times 3. And then finally, the last entry, this last row times this column, 3 times negative 1 plus 1 times 3. So there's the output. So of course you do the arithmetic here. So what this is -1. This is what, 13? This is 0. So A times B is another matrix, in particular vector. It's the vector consisting of -1 and 13 and 0. So that's how you multiply a matrix times a vector. Matrix times a vector is just this operation with your fingers where you click through and add is clicking, and move to the next row, move to the next row, and so on. And in the end, you will have built a new vector. Matrix times vector is vector. Okay, so anyway, as you can imagine, it's kind of hard to explain that in text, because really you're watching your fingers move, your hands move. Any questions on that? Okay, you guys do this one. Do this matrix times this vector. Take 3 or 4 minutes to do that. So you're always going to start with the first row. For sure. Yep. I'm just going to write it up here, so if you're not done yet, you can just shoot. So is that what you guys got? Any issues with that? Okay, so you should really sort of do a gut check at the end just to make sure, like, this was 3 by 3, that's 3 by 1. So 3 by 1 is what popped out. That's what should have happened. Okay, so that's how multiplication works with a matrix and a vector. Now, of course, like in the homework or whatever, we're not gonna have questions like this because we don't really care about this for our purposes. We care about it because later it'll help us rewrite some systems of DEs. But anyway, you have to be able to do that to rewrite the systems of DEs. Okay, so just as an aside here, not a very long aside, but again, I just want to mention this from Wednesday, that you've already seen a sort of like this kind of multiplication if you saw this in high school, this matrix way of viewing these equations in high school. So let me just show you that real quick. So we just briefly mentioned this at the end of class on Wednesday, but consider that system of equations there. That's a 2x2 system, 2 equations, 2 unknowns. Just at the end of class Wednesday, I said, hey, you could reconceptualize that as a matrix equation like this. You build a coefficient matrix. Right, the nice thing about linear algebra is everything you say sounds fancy and impressive, right? Don't you agree coefficient matrix sounds fancy? No? I think it sounds fancy. Okay, so the question is, why is this? Why is what I wrote on the board here equivalent to that? What was on the screen? And the answer is, well, look, suppose I asked you, hey, on the left-hand side here, do the multiplication. Like this is A, this is X, like that, vector X. If I asked you to do this multiplication here, let's just do it. AX equals what? It's going to be a 2x1 matrix. What's the top entry here? If you do that thing we just said, right, 2x minus 5y, and then the bottom entry is x plus 4y. Okay? So you're saying this left-hand side is this vector, and that's supposed to equal this right-hand side? Well, as it says up higher in the handout, the only way for 2 matrices to be equal is if all their entries are equal. So all you're really asserting here is that 2x minus 5y is 3, and x plus 4y equals 2. So way back up here. That's what that equation is saying when you boil it down, right? You're just saying that whatever x and y are, 2x minus 5y must be 3, and x plus 4y must be 2. You've just written it matrix style. But it's encoding the same system of equations for you. It means the same thing. Everybody okay with that? Because of this notion of multiplication, right? You multiply this by this, you recover that system of equations. So those of you who did this in high school, you exploited this, right? Okay, any questions on that? Okay, so maybe let's skip this one, but just pointing out, you can play the same game with any system of equations from algebra 2. It's just in that case, you'd have a 3x3 coefficient matrix. Everybody agree with that? So you'd say what? 1, 1, negative 2, and then 2, 0, 3, right? No y. Negative 9, negative 1, 14. Column x, y, z has to equal 6, 10, 0. Right, so just that's how you make a matrix equation out of it. Okay. So just like in algebra 2, again, if you didn't do this, it's fine. But in algebra 2, if you make this move, it's helpful. Your calculator can handle it more easily, things like that. We're going to make the same move here in class today by the end of the section, starting with a system of D's, rewriting it as a matrix equation. It makes things much simpler once you get that notation down. Okay, lastly, you can multiply a matrix by a scalar. And by scalar here, I just mean a constant or a function of t if you want. So it doesn't have to be literally a 5 or whatever. So if C is a scalar and A is a matrix, you can multiply a scalar by a matrix, or you just multiply everything in sight by that scalar. So we're not going to be using that exactly. We're actually going to be using sort of the inverse of that. So here's a matrix here. It's a vector, but it's a matrix, right? A 3x1 matrix. What's a better way to write this if you don't want to write it out like this? What's a simpler way to write it? Sorry for those of you who I'm recording this for, this one. Yeah. Yeah, good, right? So if you can multiply everything by C, you can also factor that C out if you want. So like this. Precisely what Cody said. You can take that e to the t and factor it out. So you can rewrite it like this. E to the t and then 3 negative 2's. That's the same thing as what's on the screen. Is that okay? Okay, so that's actually all the notation we need from 7.2, all the notions we need. Again, if you read section 7.2, which if you're bored this weekend, you can, they talk about Hermitian matrices, the identity matrix, inverses, all sorts of stuff, right? We don't really need any of that. The last thing we need from that section, though, is this. You can take a derivative of a matrix if you want to, which suddenly seems now more relevant to us, right? You can do calculus with matrices if you want to, and it turns out we will want to. So the derivative of a matrix is, like, if I asked you to guess without having the derivative, the definition there, it's precisely what you think it would be. You know, you go in and you differentiate everything you see. Everybody see that? So like if I just handed this to you cold, this guy right here, whoop, share this. If I just handed this to you cold and said, what's this thing's derivative? What would you do? If you had to just take a guess, like how, if I haven't told you anything, but I said, hey, differentiate that 3x1 matrix, what would you do? Yeah, you just go to each individual piece and differentiate, right? And it turns out that's what you do. Yeah.
In this example, you're also taking out, differentiate the t, and then multiply that.
Yeah. So Ben's question was, could we take the e to the t out first, then differentiate, and then put stuff back in? Yeah, you can do that. Yeah. So anyway, that's all the derivative of a matrix is, just the derivative of the individual components. So this guy's derivative is itself, right? But if you had like a sine up here, you change it to a cosine, whatever. Okay, so basically we're now done with 7.2. I just want to show you now the most important part of 7.2. It's only a notational thing. So it's just a way of rewriting things, but that's why we're doing 7.2. So I'm gonna have to stop sharing my screen here in a second, but okay, the question is, here I have a 2x2 system of equations. As we talked about on Wednesday, there are two unknowns and two equations here. The unknowns are function x1 and function x2, both of which are functions of time. Everybody agree with that? You could, if you wanted to, solve this by substitution, as we did on Wednesday. You could be like, I'm gonna isolate, I guess, x2, no, I can't do that. Isolate x2 here, I guess. Right, or isolate x1 there, whichever choice you want to make, and then off we go like we did on Wednesday. Y'all remember doing that? Yesterday wasn't a spring break day, right? So you remember Wednesday. Okay, so now let me show you how you rewrite this matrix style though. So maybe you don't have to use substitution if you don't want to. Okay. So again, this seems like almost a trivial move to make and almost not even worth the price of admission. Like, why bother with matrices if I'm just rewriting things? But it turns out it will be incredibly useful, as we will see on Monday. Okay, so I'm going to rewrite that equation like this. And I'll see what you think about it. If I can see through the glare, I'll rewrite it. So there used to be two equations. Now there's not. Now there's only one equation. So just like in algebra 2, right? With this example, whatever it was, the algebra 2 aside, I started with two equations. I end up with a single matrix equation. I've done the same thing here. Now the question is, what is this? And how does it represent that? Why are they equivalent? Okay. So the first thing to recall is that if somebody writes down something like this, vector, the individual entries are always labeled like this, and it's understood things are two-dimensional here. So if you ever see an X with an arrow over it, the first entry is always X1, the second entry is always X2. If there were a third entry, it'd be X3, and so on. Therefore, if somebody says, well, hey, the vector X derivative, what's that? Yeah, we said above, well, the derivative of any matrix is just individually differentiate the components, you know. Okay, so back up here, X arrow prime, that's just a faster way of writing X1 prime, X2 prime as individual entries inside of a vector. Now, on this right-hand side, let's unpack what this is saying. 3, -2, 5, -1. Vector X, but vector X is like this. right? If I just gave this to you and said, hey, multiply this matrix by this vector, what vector would pop out over here?
3x1 minus 2x2.
Hey, are you just, again, put your fingers in and click like that?
5x1 minus 2.
Yeah, sorry, negative 1, right?
Just minus x2.
Yeah, like that. So this right-hand side is a faster way of writing this. These are the same thing. And you know, this left-hand side here, this x arrow prime, is a faster way of writing this. Those are the same thing. So ultimately, what I'm asserting, like by writing this equation down that I started with, what I'm asserting is this vector here, circled in green, this vector equals this red vector over here. But if this vector here is supposed to equal this vector over here, you see? I'm just saying x1 prime, top entry equals top entry, equals 3x1 minus x2. But that's one of the equations I started with. And then I'm simultaneously saying this bottom entry must equal this bottom entry. Everybody see that? I've taken that 2x2 system there and I've just written it in a different way, but equivalent way, you know? Those two equations are literally asserting, right? x1 prime must be 3x1 minus 2x2 and so on. If this is going to equal this, x1 prime must be 3x1 minus 2x2. It's just encoding the same information, but it's encoding it in a more compact, matrixified form. Everybody okay with that? Okay, well, we'll see. I want you guys to take this, example 7, rewrite it as a matrix equation. So you want to write down something like this. Any issues with this? Were you guys able to do it? Somebody just shout out. What's the matrix version of that example 7? Derivative of x vector, right? That's fine. You can shout out whatever. That is the left-hand side. You can condense down like that, right? Derivative of x1, x2. What happens on the right-hand side?
Well, you're going to have vector 4, or not vector, matrix of 4 and then 1, 3, negative 5. I don't know what I'm saying.
Yeah. So what you need to have on the right-hand side is something that will turn into 4x1 plus x2, right? So how do I fill that in on the right? Yeah, so I mean, you could just literally write this if you wanted to, right? 4x1, x2, and then down below 3x1 minus 5x2, right? But again, we're trying to like write things as compactified as possible. So what Cody said, vector x. So again, that's the end of section 7.2. Really. Just can you take a 2x2 system and reconceptualize it as a matrix system? And if you can't do that, then the rest of the chapter actually makes no sense. So it's actually not the case right now. You have to understand everything. But by the time we get to like section 7.4 or 5, if you don't understand this notation, just literally nothing makes sense. So let me just pause here and ask again. Do you see why this equation here means the same thing as those two equations up top there? Okay, so let's do one last example. This is example 8. So rewriting this system of these as a matrix equation. So you want a single equals and matrices floating around. The left-hand side, I think you'll agree, will still be x vector prime. What about the right-hand side? What changed over there? Yeah, there's now sort of extra stuff there at the end, right? So what if the 1 and the t weren't there? What would you write down?
Matrix 4, 3, 0, negative.
4, 3, 0, right? Because there's no x1 term, -1, like that. Does everybody agree with that? No 1 and no t is what you'd write. But of course, there are a 1 and a t added on to the end. So can anybody think of a matrixy way to take care of that?
Add matrix, or yeah, add matrix 1.
Yeah. So there's a matrix equation. So the derivative of x has to be this matrix times this vector plus that vector. And again, you can check if this makes sense by just, you can always take the matrix thing and go back to the original to check if it makes sense. So I'm going to write everything out explicitly so we can see that. Okay, so on the right-hand side, I have matrix times vector, which would give me a 2-by-1 vector if I multiply them, right? I get 4x1 plus 3x2, and then bottom entry would be the other one, and then that would be plus 1. So I can take this notation, just read across the top. I can be like, okay, so x1 prime, that has to equal 4x1 plus 3x2 like that, plus a 1. Basically, you're reading literally across the top. I have a 2-by-1 here. I could make a 2-by-1 over here if I combined everything, you know. And then same thing with x2 prime. x2 prime has to be 0, -1, x1, x2 like that, plus t. That's what is set up there, right? So again, this looks intimidating since we haven't done it yet. And it looks unnecessary, actually, right? But it is equivalent to the original two equations, which is more condensed. And that's the end of section 7.2. Questions or comments on that? So this is the main takeaway. Can you start here and reconceptualize it like we did? Is everybody okay with that? Okay, now section 7.3, given what we need, is actually even shorter. So we actually only have this much left on the handout, right? Section 7.3, again, is quite long, actually. There's a lot of linear algebra they want you to learn there that we just don't need for our purposes in this course. So section 7.3, the only concepts we need for our purposes is the concept of an eigenvalue and an eigenvector. So what do those things mean, right? Those sound even fancier than other things, right? Eigenvector, I don't know, that sounds pretty fancy. So rather than just giving you a definition, I want to motivate what they mean by having you think about this particular matrix here and multiply it by some vectors. So this is extra multiplication practice. So take like 5 minutes to do capital A times little a, capital A times little b, and so on, and see what vectors fall out of that. So do those 6 separate multiplications for the next 5 minutes or so. Riley or Pedro, you guys okay?
Yeah, I'm good.
Okay.
Same here.
So you guys finished maybe half of them. All right, so if you haven't finished, that's fine. You just check the answers against the ones we have. So just walking around, I don't remember the answers. These look right to me though, based on my memory. You guys get 5-7 for the first one, 3-0 for the next one, 6-6, 15-15. And then what happens with these? Okay. So one way you could view that matrix A, you could view it as a vector transformer or something. So when matrix A sees this 1-3, it's like, oh, I see your 1-3, I'll give you a 5-7 back. Everybody see that? Oh, I see your 2-1, I'll give you a 3-0 back. So this matrix, this vector enters and this vector comes out, like a function, input, output. This vector comes in, this vector comes out, and so on, right? Now, some vectors, when they go in, something sort of special or unique happens. Like, what do you notice about some of these? Say again, sorry?
It has the same top and bottom. It'll have the same, or the vector has the same top and bottom. Come out is the same.
Yeah. So here's one observation. Jacob was saying, well, if top and bottom match before, they still match after, right? You see that? That appears to be happening. I mean, we only have 2 data points, right? So that's not a proof or something, but that seems to be what's happening. So one way you could phrase it is, oh, if I input a vector that happens to look like this, and what does look like this mean? It means like this. A, right? Match, right? If I enter a vector that looks like that, what seems to be happening is this vector pops up. Tripling, And that kind of thing did not happen here, right? So a 1 went to a 5, a 3 went to a 7. There was no scale factor there that matched up. Or here, 2 went to a 3. So that was multiplication by 3 halves, I guess. And then -1 went to a 0, multiplication by 0. There's no scale factor that matched both. But here, top entry and bottom entry are both scaled by 3. So visually, I'm running out of room, but visually what's happening is this. Okay, so 2-2, 1-2, 1-2. This is 2-2. It's just literally importing at the point 2-2. you fed that arrow into the matrix, you fed that vector into the matrix, and the matrix says, oh, okay, I see your 2, 2. I'm going to give you this vector back. Something parallel to the original arrow. You're okay with that? If you think of 2, 2 as just this vector, the way you normally think of vectors as arrows. Okay, this part right here is 2, 2. 6, 6. So anyway, when the matrix saw 2, 2, it was like, okay, I'll give you 6, 6 back. I'm just going to stretch the arrow for you, but I'm not going to rotate it at all. In contrast, what, 1, 3? 1, 3 is like this. When the matrix saw 1, 3, it was like, okay, I'll give you 5, 7 back. 5, 7 is like, wait, did I say that backward? 1, 2, 3, 4, 5. So it's up here somewhere. So the original black arrow was not just stretched or something, right? The output's not parallel to the original input. So all of that to say, some vectors, when you feed them into that matrix, the matrix sees your vector and it gives you another vector back that's parallel to the original one. Everybody see that? You just scaled it, you know? Just literally said, oh, multiply by 3, multiply by 3. So visually, that's just a stretch of an arrow. And the same kind of thing happened for, I didn't switch those, right? 1, -1 became 1, -1. Is that right?
Yeah.
Yeah, so in that case, that's sort of the most extreme thing that could happen. So 1, -1. The matrix was like, oh, 1, -1. You know what I'll give you back? I'll give you back 1, -1. You know? So not just parallel, but actually equal, you know? Okay, all that to say, there's special language for vectors that are like that. So you have a matrix in mind, which we did here. So you have to start with some matrix you're working with. If you have a matrix in mind, vectors that operate like this, like 2, 2, 5, 5, so A, -A, and also what? These vectors look like A, -A like that. So AA or A, -A, vectors like that, right? When the matrix sees those things, it gives you either the literal vector back or stretches it for you. These things are called eigenvectors. So an eigenvector is a vector that the matrix just scales. It doesn't rotate. So when you feed the vector in, what comes back out is a multiple of the matrix. Or sorry, multiple of the original vector. So the matrix could stretch it by 3, could leave it alone, as we've already seen. It could cut it in half, that's a scale. It could also multiply by, say, -2, which would double the length and then flip over the origin. That's still parallel, though. So anyway, that's the idea of an eigenvector. So let me just put up a formal definition here. Which I think, oh, so formal definition is up here, yeah. Okay, so if you have a matrix going, so let A be a matrix, a vector B is said to be an eigenvector if A times B is parallel to B. So you feed B in and A gives you a multiple of B back. So in other words, A times B is just some scalar multiple of B. So all it's saying there is there's some stretch factor, you know, like maybe you triple, maybe you quadruple, maybe you cut in half, I don't know. So again, on the board here, 1, 3, and 2, -1 aren't like that, right? You fed those vectors in, the matrix didn't just stretch them. It like stretched and also rotated. But 1, -1 got stretched by a factor of 1. 2, 2 got stretched by a factor of 3. Okay, so once you have the notion of eigenvector, you can then ask, well, what was the stretch factor? Did it double? Whatever. The stretch factor is called an eigenvalue. So all that to say, erase all this. With this new terminology, we can say this. We can say vectors A are eigenvectors of that original matrix big A. Anything that looks like AA, so 2, 2, 3, 3, 4, 4, whatever, -1, -1. And furthermore, eigenvalue corresponding to those eigenvalue corresponding to AA is 3. So these vectors got stretched. How much did they get stretched? They got stretched by 3. The eigenvalue is the stretch value. Eigenvectors are the vectors being stretched, being scaled, however you want to say it. Okay, so all that to say, eigenvectors come in families. Everybody see that? Like 2, 2 was in the same family as, what was it? 5, 5, right? And 1, -1 is in the same family as 3, -3. And every family comes with a stretch factor. That's just called an eigenvalue. Everybody see that? I mean, does the definition make sense? I guess is all I'm asking. So this term makes sense, and this term makes sense. Okay. So it turns out that solving, if you want to solve a system like this, or a system like this, actually, but really we're going to focus on these for a while. You want to solve a system like that. It turns out that finding eigenvalues and eigenvectors will tell you everything you need to know. Eigenvalues and eigenvectors of what? The coefficient matrix, so 4, 1, 3, -5. Okay. Now, of course, it's not obvious why that would be true at all. What does stretching vectors but not rotate them, what does that have to do with anything? What does that have to do with this calculus problem, you know? And the answer is get off my back for a second, right? You'll see on Monday, you know? We only have so much time today, you know? Anyway, so for now, if finding eigenvalues and eigenvectors is what we have to do to get back to the differential equations, a natural way to end this section is to like ask, given a matrix, like suppose this was a coefficient matrix and it came from something like this. Given a matrix, how do you find eigenvalues and eigenvectors? Everybody see that? If that's something you need to know, that's a linear algebra question. Everybody see that? Then the question is, well, how would you do that? And it's very similar to me asking you like, hey, back in chapter 3, we had a calculus problem and then we wrote down an algebra problem, like r squared plus 5r plus 6 or whatever, right, equals 0. And then we had to solve that problem. You know, that was purely an algebra problem. And what did we do back then? Yeah, once you had the r's in place. Yeah, you gave it to the computer, right? Because we're not focused on the algebra. So same thing here. This is not a linear algebra course. If you take that course, you'll learn in like complete detail how you find eigenvalues and eigenvectors of a matrix. And it's interesting. I mean, I don't want to downplay it, but for us, it's just not worth our time. So what you will do is, once you know the matrix you have in mind, you will scurry off to Wolfram. Wolfram, of course, has a command like this. See, I was already trying to autofill for me, right? Now you'll notice it gives you the syntax at once. So you have to, if you want the eigenvalues of a matrix, you have to, of course, give Wolfram the matrix, right? Here's how it wants the matrix. Outer brace, outer brace. That's saying I'm beginning a matrix, I'm ending a matrix. And then to the curly braces inside, curly braces, this is each thing is a row here. So the top row is 4, 1. The second row is 2, -1, and so on. So you can add as many rows as you want. You just have to separate them with commas. So here's the syntax for the one on the handout. Eigenvalues. So I'm going to handle the first row like this, 3, -1. Close that brace because the first row is done. Comma, because I'm moving on to the next row, 4, -2. And again, if you forget the syntax, Wolfram is going to try to autofill it for you beneath, you know, so you can see the syntax if you want. So then you hit enter, and it does the linear algebra that we're not covering, and it gives you results, right? It says, hey, there's going to be a stretch factor of 2, so some vectors will just be double. there'll also be a stretch factor of -1. So some vectors will just be reflected across the origin, but not stretched at all. And then you can ask, oh, which vectors are double? And Wolfram says, vectors that look like this. So as we've already pointed out, eigenvectors come in families. So Wolfram doesn't give you the entire family, it just gives you a representative sample of the family. So here it's saying anything that looks like top entry matches bottom entry. It gives you the vectors horizontally, I guess I should say, right? But we write them vertically, but anyway. So it's saying, hey, any vector where top and bottom match, it's gonna double that for you. Any vector where the bottom entry is quadruple the top vector, that's gonna get stretched by a factor of -1. So let me just come back here and summarize what else Wolfram has told you. And then we'll actually be in a position to go back to differential equations and systems on Monday. So Wolfram has told you this. All vectors form A are eigenvectors, which I get tired of writing, so I write evex. These are eigenvectors with eigenvalue. So the stretch factor is 2. And then it's also told you this. All vectors of the form not top and bottom match, but the bottom is quadruple the top. Are eigenvectors with stretch factor not doubling, but -1. So as with any of these things that we do on the computer like this, you just have to know how to type it in and then know how to interpret it. So for now, this is the only interpretation we need because we're not doing any calculus right now. But then on Monday, we'll have to know how to slot these into the solution of the system of the differential equation. Okay, so that's section 7.2 and 7.3, what we need of them. So in the homework, there are questions that are like, hey, here's a matrix. What are the eigenvalues and eigenvectors? The book will show you how to get those things by hand, you know. You should not read that unless, again, you want to. You're bored, right? You can read that, but that's purely an algebra problem. So really, I just want you to have practice, like make sure you can type this in and get the results back, you know. So to summarize today, what you need to be able to do moving forward is take something like this and reconceptualize it as a matrix equation. We did that, right? Once you've done that, you then need to be able to take the matrix you've gotten, hand it to Wolfram, and get this information and know what it means. If you can do that, we can go back to the calculus on Monday. So any questions or concerns about that? Everybody's okay with that? You feel like you can do this sort of thing in the homework? Okay, have a good weekend. You're all looking at me expectantly. Was I supposed to give you something or something? No? All right. Like you look like you want more. I have no more to give today.